Okay. All right. I'd like to thank the organizers for this opportunity to participate in a friendly debate about dark matter and alternatives. I'm going to try to speak, pretty broadly about the reasons why the particle physics and cosmological communities have become so convinced that dark matter is a major part of our universe over the last several decades. And I'm going to try to give some of my personal arguments for why I think these arguments are so compelling, and maybe a little both historical and otherwise personal thoughts about how this all fits together. So I'm going to start by saying what sort of things I'm setting out to argue in this talk, okay? Because there's some things that you might think I'm prepared to argue that I'm not, and I want to make clear exactly what the case I'm trying to make. So first of all, I'm going to argue that the case for dark matter is on extremely strong empirical footing. We measure the existence of dark matter in numerous different ways and in different kinds of observations and different kinds of scales. And all of those lead to a concordance in favor of something like the standard lambda CDM cosmology. If we're just talking about discovering the existence of dark matter, not the nature of it, we've discovered dark matter in a lot of different ways already, exceeding all kinds of statistical and other sorts of criteria you might apply. Although we don't know what the stuff is yet, so I don't want to make this statement be misunderstood. In contrast to all the successes of dark matter in more broadly speaking, lambda CDM cosmology, no proposed version of MOND or any other modifications of general relativity that are intended to do away with the need for dark matter have been able to explain either the large-scale structure of our universe or the cosmic molecular background. Of course, Eric was clear in his talk that he doesn't have a complete theory yet, so he can't make these sorts of predictions. But I would, if I took two alternative hypotheses, one of which makes very clear predictions, which precisely agree with all observations, and the other which doesn't make predictions on most scales of interest, I think you know how that would turn out in some sort of Bayesian framework. All right, so here are some things I am not going to try to argue in the course of this talk. So I'm not going to argue something stupid like it's entirely impossible that observations we currently attribute to dark matter are actually somehow the consequence of some departure from GR. Science doesn't work that way. All scientific truths are contingent or provisional. This is no exception. But I am going to argue that this is pretty unlikely. I would say highly unlikely. I'm also not going to argue anything silly like that no one should be working on MOND or any other modifications of gravity. This is real science. It's not like doing astrology or Freudian psychology or something. This is stuff that scientists should be working on. It's a legitimate scientific endeavor, and I wish them all the luck in making progress. So these two, if I were trying to argue these things, I would say that I'd be arguing against a strawman. So this is not the sort of thing that I'm trying to argue here. All right, so a little bit of history. So you've probably seen all these talks that I've seen too. I've been doing dark matter a long time, but so many talks, seminars, conference talks, and colloquia start with one slide on dark matter in which these two pictures appear over and over and over again, okay? That is less an accurate history of how dark matter became the established paradigm and much more mythology. It comes down to telling an oversimplified story in hindsight, not taking into account how things actually played out. This is not to say that Zwicky and Rubin didn't make important contributions, but they of course did. But it wasn't the dynamics of galaxies or even galaxy clusters that led to this broad consensus that dark matter exists. In fact, it's interesting note that neither Zwicky nor Rubin were actually convinced by their own observations that dark matter exists. If you go back and read the papers that we cite as early papers on particle dark matter, you'll be surprised to learn that most of them don't make any reference to any kind of dark matter problem. Okay? So I'm talking about papers in the 70s and the first half of the 80s. At this time, these papers weren't about any missing mass in galaxies or clusters or anywhere else in the universe. They were just trying to put cosmological constraints on their particle physics theories. The authors were at the time, I would say, either unaware of these issues or unconcerned with them. Take, for example, the famous Lee and Weinberg paper of 1977, basically heavy Dirac neutrinos as dark matter, more or less. The only time that they make anything close to a statement about dark matter is this quote: "Of course, if a stable heavy lepton were discovered with a mass in this range, the gravitational field of these heavy neutrinos would provide a plausible mechanism for closing the universe. They don't say anything about galaxies or clusters or dark matter or missing mass. If they were aware of those problems at all, they didn't take them seriously enough to mention it in their paper. That wasn't what this paper was about. It wasn't until roughly the mid-'80s that most of the papers that particle physicists and particle astrophysicists were writing on cosmology of their models made any reference to these sorts of issues. So many of these early papers on things like neutralinos and axions that we now think about being about dark matter, in fact, made no reference at all to any kind of missing mass problem. The necessity of dark matter became a consensus view only much later. All right, so what changed this? So what convinced so many scientists that the dark matter should be the established paradigm? Well, I can't give you a complete list, but here are some of the important things that happened between the mid-'80s and
it wasn't the mid-'80s, it was earlier. I mean, the neutrino, the Lubimov experiment with the 30 eV
the incorrect 30 eV neutrino mass measurement in 1980 was important. I agree.
Yeah, so it's earlier. It's not.
Well, I mean, okay, it wasn't a step function in time.
Cold, warm, dark matter. That nomenclature was invented by Dick Bond in 1981.
So if you take, but I've read all the papers, right? So if you go to 1982 and read the top 20 cited papers that we now think about being on dark matter, maybe 2 or 3 of them ever mention a missing mass problem.
Well, we know citations are not an indication.
I'm not talking about citations. I'm talking about the language of the papers, what the papers actually say.
Well, I mean, the Saleh and Cleveland and all these people, McClellan, sorry.
Yep.
They were all.
Kausick and McClellan?
Yeah.
No, I mean that.
Kausick is even earlier, right?
Yeah, that was 1972.
Right.
Yeah, but they don't talk about any of that. They don't cite Rubin. They don't think about Zwicky. None of this stuff was on their radar.
No, but the Lubimov experiment that was wrong. That's all about dark matter, and that's 1982.
Okay, so we'll talk more about it. But it was certainly the case that in 1982 most physicists weren't convinced that they needed exotic physics to explain dark matter. Most were not. Okay. So what changed that? So large-scale structure, which of course you know a ton about, played a big role. So it was in the mid-'80s that you started to see that the galaxy surveys, okay, that described the large-scale structure of our universe, could only match simulations if you included cold dark matter. This was important because it ruled out hot dark matter, and it also it didn't suggest that there was just machos or some sort of other baryonic matter that was responsible. In 1982, as far as I'm aware, this was the first time it was pointed out by Jim Peebles that the absence of fluctuations, temperature fluctuations, at a level of 10 to the minus 4 in the CMB was incompatible with a universe that consisted of only baryonic matter. And maybe in 1982 this wasn't that overwhelming yet, but in the years leading up to Kobe, this got more and more compelling. So it was the CMB, even early on, that was pushing this sort of consensus view. Thirdly, it was in the late 90s that Eros and Macho really made it clear that most of the missing mass wasn't in the form of compact baryons or baryonic objects, with, of course, a couple of windows that we have already talked about today as exceptions. And then overall, the tightening of the baryon budget was important. So BBN in the 70s told us that we were in an omega-1 universe with baryons, but it could still be 0.1 or maybe even 0.2. But by the 1990s, it got really tight, okay? The baryonic density was only 4% or something, and that was incompatible with all these other dynamical requirements. So the point of this history is to emphasize that galactic dynamics didn't have a whole lot to do with the rise of the consensus paradigm of cold dark matter. Cosmological considerations played a very important role at every step along the way. All right. So that brings us to the age of precision cosmology, which is what any alternative to dark matter really has to face. And this is where the really big challenges come in. Of course, this is the power spectrum of the CMB, the temperature fluctuations. I mean, you can't even see the error bars, right? I mean, here you can, but they're literally smaller than the points. It's amazing, right? You can measure all sorts of things by measuring as many of these peaks as possible. You can measure the geometry of the universe, the amount of dark matter, dark energy, and dark matter, baryonic matter, and dark energy, among other things. Here's just one of the parameter tables in the Planck paper. Here's the dark matter abundance. And the amazing thing, the thing that you should if you want to explain these observations without dark matter, you have to reconcile, is that this number is the same number you would get from any other or any number of different ways of deriving the cosmological abundance of dark matter. So if you look at clusters and measure the dark matter abundance that way, you get the same number. If you measure the large-scale structure in your simulations, you get the same number. If the concordance between these very different kinds of observations on very different scales all give you the same cosmological parameters up and down the board. That is a big part of what makes lambda CDM cosmology so compelling. So let's talk about the CMB and what it really tells us about the presence of dark matter. So in particular, it tells us that the inhomogeneities in the photon baryon plasma were at a level of 1 part in roughly 10 to the 4 at the time of recombination. That's the first approximation what it tells us. GR, without dark matter I mean, predicts that such inhomogeneities would have grown by about a factor of 1,000 since. So you're going to take 1 part in 10 to the 4 to 1 part in 10 or so. 1 part in 10 is not particularly large in terms of inhomogeneities. In other words, what that combination tells us that if there wasn't dark matter, large-scale structures, we know it would have never formed. We would live in a approximately homogeneous universe today, which of course we don't. In any scenario without dark matter, you'd have to somehow make your modifications of gravity drive the perturbations to grow faster than GR predicts. Okay? You can do that. There are lots of ways to do that. Just for example, in the Bekenstein-Tevis theory, the vector field can drive a difference between the two scalar gravitational potentials, leading to the enhanced growth of density perturbations. This was calculated by Scott Dodelson in 2006. And when you do that, you can explain the first and second peaks. Okay, so in the first 2 peaks of the CMB power spectrum, you can get by doing something like what Dodelson and Liguori did within the Bekenstein framework, but you can't get the 3rd peak. So here's the result from the study shortly after Tevis came out by Konstantinos Skouras and Slim Bohm and I think Joe Silk and I forget who else, but that group at Oxford. And the point here is that you have a prediction for lambda CDM, which is the dotted line here. Okay? And then you have a prediction for MOND, which the first 2 peaks work great, and then it's suppressed beyond that. And also I'll point out here that they really cranked up the neutrino cosmological role of neutrinos, and that's totally ruled out now. But at the time, you could push it up to that sort of level. So in 2005, when this plot was made, you could make this kind of marginally consistent with WMAP. This was very encouraging from a Tevis sort of perspective. But if you try to do it now, you just don't get anywhere close. So this is the Planck data, and this is a superimposing the Skouras et al. Result. And you can see that you get the first 2 peaks reasonably well, and then you're way below observations. And I mean, this is, I don't know how many tens of sigma, but it is an absolutely terrible fit to the data. And this is with enhanced structure growth. So it's not just a matter of getting the structure growth to happen. You can do that in various Mondian frameworks, but you can't explain the 3rd and subsequent peaks. So that's a big enough problem on its own, but it's not the biggest problem for MOND observationally. The biggest problem, as I see it, and I'm basically channeling Scott Dodelson here. He wrote a really beautiful paper on this. But the matter power spectrum is even harder to explain within a context of MOND. So we measured this matter power spectrum from scales all the way to the cosmic horizon, 10 gigaparsecs or so, down to megaparsec scales, the scale of galaxies, and they're in beautiful agreement with the predictions of standard lambda CDM. You can see it across many, many different orders of magnitude. If you look closely, and the data kind of obscure it, but there are little wiggles in this, and those are the baryon acoustic oscillations. In standard lambda CDM cosmology, these baryon acoustic oscillations are small. They're small wiggles precisely because as the baryons fall into the potential wells formed by dark matter, only a few % of the primordial oscillations survive. So the dark matter suppresses or damps these oscillations. So the point that Scott made was that if it weren't for the dark matter, these oscillations should look like this. Okay? They should be wildly bigger than the tiny little oscillations that we've observed in the matter power spectrum. So by about a factor of roughly 30. So in a universe without dark matter, the BAO should have been the first thing you saw when you measured the matter power spectrum. It shouldn't have been a recent discovery. We should have known about it a long, long time ago. And if you have an alternative to dark matter, you need to somehow explain that. And I've never heard any proponent of MOND have a good explanation for even in principle how that sort of thing could work out. All right, the third piece of data that of course everyone's familiar with are the bullet cluster, more generally speaking, cluster dynamics. I don't think I have anything to add to this. Everybody's heard this argument many, many times. I'm just going to say that that's another a very big challenge for various forms of MOND. All right, so in light of these challenges that I've laid out and others, you might have guessed that interest in MOND would have declined as precision cosmological data has become available over the last couple of decades. But this is what happened instead. So it's an imperfect measure, but it's a reasonable one. So I took Milgram's original 1984 paper and just asked Inspire to tell me how many times it was cited in each year. And, it was just a few times. And then right around the time the age of precision cosmology started, it shot up. This is, in the year 2000, I think one could have made a pretty credible case for something like MOND because we didn't have the kind of precision cosmological data yet. But just about the time that we had the data to really challenge it, interest in it exploded. So I became really interested to try to figure out what sociologically drove that drive or that enhancement. And I still don't really know the answer, but my guess is it has to do with the small-scale structure problems that people have been exploring in CDM. So it might also have to do with the fact that we haven't seen dark matter particles, and if you're thinking in a SUSY framework or something, you might have expected us to or something. But maybe it's a small-scale structure problem. So I thought I would spend a few minutes talking about those issues. We'll start with the missing satellites problem. I think this is an appropriate prefactor to that, given the current situation. But back in the late 90s, it seemed to be a real problem. It was pointed out back then by Klippen and Moore and others that in dark matter-only simulations, you should expect a Milky Way-like galaxy to have hundreds or maybe 1,000 satellite galaxies, and only something like 10 had been observed. These are the classical dwarfs. But since then, a bunch of surveys have led to the discovery of, instead of 10, more like 50. And also, we expect, we understand baryonic physics and its role in a much more important way now. It's now clear that in most subhalos below 10 to the billion solar masses or so, these aren't going to efficiently form stars, explaining why we haven't seen them. If you want a good argument, I'll point you to Annika's beautiful paper from just last year. They make a very compelling case that the data we have is entirely compatible with what we expect within an ordinary lambda CDM context. Here's an example from this paper comparing the results of a dark matter-only simulation on the left to a hydro simulation that includes the effects of baryons. You can see that the baryonic effects do lead to less small-scale structure, exactly consistent with observations. The second problem that has received a lot of attention in the last, let's say, 7 years is the too big to fail problem. Michael Bolen-Kolchin and James Bullock and Manoj Kaplan pointed out that in lambda CDM simulations, these tend to predict more very massive, so 10 billion solar mass or more, satellite galaxies that are observed. And even if baryonic processes somehow suppress star formation in these systems, it's hard to imagine that something that big wouldn't have stars in it. So that's the premise of the problem. There are a couple of ways that this might get resolved. On the one hand, if the Milky Way's total mass is on the low side of current estimates, and here's one recent paper that has a pretty low value, it would just make us a mild outlier. So it might not be a problem at all in that sense. And then also, there's been a lot of work about how baryonic effects will impact this as well. For example, here's some stuff by Alison Brooks and others and collaborators. Alison's around somewhere, hello. So in these papers, they show that baryons can cool, moving mass toward the center of the parent halo and creating strong tidal forces that bring these 10 to the 10 solar mass objects down to smaller masses, relaxing or alleviating the problem. Also, the presence of the galactic disk alone, which of course isn't present in dark matter-only simulations, will destroy something like a third of these very massive satellites. All right, and the third problem I'll briefly mention are the cores and cusps. In dark matter-only simulations, halos generally feature inner regions with high-density cusps, where some observations seem to favor shallower profiles or even flat density cores. But more recent work doing hydro stuff has shown that stellar feedback can lead to repeated fluctuations of gravitational potentials in these systems, removing dark matter from the innermost kiloparsec. Here's a result from Decentio et al. For Milky Way-like objects, you might expect a cusp, and for ultra-faints, you might expect a cusp, but in between, the hydro effects can flatten these objects' profiles, explaining the cores that are observed. So, taking all these things together, my personal opinion is that baryonic physics is probably going to resolve all these problems. We'll look back in this time and say, well, we were confused about some issues at the time, but ultimately lambda CDM wasn't in any kind of crisis. But there are a lot of smart and informed people who hold other opinions, so I am not going to tell you that you have to agree with me on this, but that's my personal view. But even if these problems are real, okay, and they're not the result of baryons, you could have small departures from cold collisionless dark matter that could very plausibly resolve these issues without resorting to something as extreme as modifications of gravity. So here's an example from one of Allison's simulations. This is the same 10 to the 10 solar mass halo in a cold dark matter, warm dark matter, and self-interacting dark matter framework. And you can see they have qualitatively different features, different kinds of halo shapes, different kinds of numbers of subhalos, different amounts of substructure. Some array of variants like this could very plausibly be responsible for the so-called small-scale structure problems. All right, so the last thing I want to talk about is I just want to ask this general question, which is, if dark matter exists, how surprised should we really be that we haven't seen its non-gravitational effects yet? This is a question that a lot of people will give you very different answers to, but I'm going to try to talk about it in a fairly sweeping manner. So I'm going to talk about it in a Bayesian framework. So the answer is going to depend very much on what your personal Bayesian priors are. So everybody take a moment and think, going back to 20 years ago, what would I, without knowing how the experiments are going to turn out, what would I have thought the likelihood of dark matter being different forms are? Okay, so you think about that for 10 seconds. But I'm going to argue that for essentially any reasonable set of priors you might have, one should be not particularly surprised that it hasn't shown up yet. Okay. So let's consider some top-down theorist, somebody who puts a lot of prior space focused on things like weak-scale SUSY, or maybe axions as a solution to a strong CDP problem, things like this. You all know people in this category. Well, SUSY's been pretty explored. I'm not saying SUSY couldn't exist or solve the hierarchy problem or whatever, but I think it's fair to say that if you're this example one top-down theorist, you would have thought it's quite likely that a SUSY exists, that you would have found it at the LHC or maybe in direct detection experiments by now. The axion is very different. This is a plot on constraints on axions taken from the early universe textbook by Mike and Rocky back in 1989. And this is still basically the picture, right? Yeah, I know ADMX just recently put some tiny little sliver of constraint in a particular mass, but basically we know just as much about QCD axions now as we did in 1989, experimentally speaking. So if you take that together, if you're this person, and you have some tens of percents on this and some tens of percents on that, your Bayesian priors haven't changed that much. The Bayes factor against your priors is an order 1 factor and nothing larger. Okay, let's consider a different person now. So this is my example 2. This isn't a top-down theorist. They don't believe you can derive all the laws of the universe on a napkin. Instead, they think you're going to measure a whole bunch of things and kind of build a scaffolding upward toward higher energy or whatever scales. Maybe they find things like the WIMP miracle to be interesting. They think some generic thermal relic might be the answer. And as time went on, they found that to save their favorite models, they had to include things like resonances and co-annihilations, or maybe go to low masses, whatever. And in the back of their mind, they've always thought hidden sector WIMPs are pretty compelling. After all, there's no reason to think the dark matter has to be charged under the standard model. Maybe as time goes on, this starts looking more and more attractive. And if you don't think that's attractive, I would challenge you to think about it this way. So there's 17 particles in the standard model. Of those 17, 7 carry QCD color. 11 carry or couple to electric charge, and 15 carry weak charge. Given that, how surprised should we really be that there would exist other particles that aren't coupled to any of this? It seems like you shouldn't be surprised at all if that turned out to be true. So I think we should be incredibly open-minded to the idea that there are hidden sectors. That is not an unnatural thing to contemplate at all. So this example 2 person, I think maybe their Bayes factor is an order unity sort of number. Neither of these sorts of figures, and no plausible set of priors I can think of should be that surprised that we haven't seen dark matter yet. All right, so pontificating for a second here. I want to say again what I am not trying to argue in this talk, because I don't want to be misunderstood. I'm certainly not trying to argue that no one should work on MOND. I do wish the people who were working on MOND would take maybe a little less interest in galactic dynamics and more interest in cosmology, because I think that's really where the work needs to be done, where the progress needs to be made. We've known since 1984 that you can explain galactic dynamics and things like the Tully-Fisher relationship and all this sort of stuff pretty well with MOND, maybe very well. But, I've been waiting the community's been waiting 35 years for a theory that could tackle the questions of cosmology with a Mondian framework, and we still don't have one. We briefly did for Tevis, but that one didn't work. So I think that's underappreciated, and certainly work is merited in that direction. When I think about the amazing successes of lambda CDM cosmology in the precision cosmology era, I think there's a very high bar that needs to be exceeded in order for a competing theory to earn the right to be taken particularly seriously. It's a very, very difficult thing to do. It's one of our most successful theories in the history of science. And it's really remarkable that we measured these quantities in so many different ways and get the same answer. It didn't have to be that way. The universe could have been much more complicated. Also, as I just argued, the fact that we haven't seen dark matter yet shouldn't surprise us that much. Maybe we think that half or 70 or 80 or even 90% of our Bayesian prior has been covered or something like that, or maybe less, I don't know. But it's not 99%. It's not 99.9%. So unless you thought that dark matter was only, very unlikely to exist at the beginning of these searches, you should still think roughly the same thing that you did then. If anything, I think we may have performed a disservice when so many of us sold these experiments over the many years by saying we're about to find it. The people who are saying in 5 years we'll discover dark matter. Somebody said that before today. Was that you, I think? Well, anyway. I did it too. I've said it over and over again. I thought the odds were good in the next 5 years we'd discover dark matter. I was never trying to deceive anybody, but probably we were being overzealous and a little optimistic in these sorts of things. I don't know how many years it will be before we discover dark matter now. But it wouldn't surprise me if it's sometime soon, and it wouldn't surprise me if it's not. I think the Bayesian priors have to be pretty broad. So I appreciate this opportunity. Thank you, Eric. And any questions, I'd be happy to take them.
So let us start with a few questions for...
Actually, this is not a question, this is a comment, Dan.
Okay.
Because you've already, this is about the history. You've got to get the history straight. Now, there's 2 points I want to make. One is, you're absolutely right that physicists in the early 80s did not take dark matter seriously, but not all of them. So Weinberg did not, but there was a great physicist who knew exactly what he was onto, and that was Zeldovich, who already argued in 1980, I can't tell you the reference, but
I agree.
That sterile neutrinos, that ordinary neutrinos with a mass of 30 electron volts were the dark matter. So that was one.
I agree.
But this lack of communication between physicists and astronomers, which was very, very severe then, persists. And let me give you another example of something you got wrong, which I want to correct. And that is the paper by Moore et al. 1999, Klippian et al., That is not the missing satellite problems. Let me tell you what it is, because Ben Moore was my student.
Isn't the name of that paper
no,
the missing satellite
no,
problem?
no. Let me explain what it is. So I don't know what the name is, but Ben was my postdoc at the time. All right. So what Ben pointed out, well, he was anyway. So point is this: Ben, the way you phrase the missing satellite problems, Ben was too smart to have made that mistake. So what Ben and George will agree with me pointed out, it's nothing to do with the number of satellites. We already knew then perfectly well that supernova feedback will make most of these halos dark. And those papers took a while to come out, but there's a spate of papers, Bullock et al. 2000, my student Andrew Benson et al. 2002, clearly showed how in galaxy formation you don't have any missing satellites problem. Ben's point and clippings was much more subtle. Had nothing to do with the number of faint satellites. It had to do with the velocity distribution, what we now call Vmax, of the satellites of the Milky Way, that at first sight didn't match the observations, even though the measurements were very crude at the time. So the point was a lot more subtle than you think. It's more closely related to Mike Boyle and Colchin's problem than it is to the missing satellites. So missing satellites have never been missing, and it is a very sad and frustrating
But you know the name of the paper
example.
you're arguing about is the missing satellites problem.
Well, missing in the sense of the velocity distribution being wrong.
Sure.
So I remember very well a discussion with Ben, where he of course understood galaxy formation. He knew that the number was not an issue.
Describing that, I think, was taken almost verbatim from the abstract of that paper.
Well,
so I don't think I'm misrepresenting
Ben, I'm sorry. Dan, I'm sorry. But go and read the paper.
You. I like this guy.
You go and read the paper.
I have.
You were reading that paper?
Of course.
Right. It had to do with the velocity distribution, not with the number.
We used velocity distribution because it could be normalized to the simulations and observations without a lot of other assumptions. But I think the critical thing in there was that if the satellites had gone missing at 10 kilometers per second, we would have, of course, attributed it to supernova and baryonic effects. But the satellites were missing at 30 to 50 kilometers per second. And so effectively it was, what people now call the too big to fail problem. This was that we realized that 30 to 50 was the issue.
I don't think we disagree, Carlos, as much as you think we do.
To put a name to the right name to the catchy name to a problem identifies. I'm not sure the too big to fail would be such a famous problem without that fantastic name. Right.
It's a trivial problem. The problem as faced by Ben is not trivial.
Yeah, I understand.
So since we're trying to debate Mond, I think Stacy has his hand up, and that's much more likely to be on that point.
Right. I think there were two people, there.
Thanks, Dan.
So we start now the debate, right?
I think we will.
You officially start the debate phase of our... Right.
Well, so I appreciate your intro slides, especially because I think if I put my cosmology hat on, I would read it exactly as you have, that there are all these reasons to believe cosmology and Mond is a non-starter.
Okay.
If I put my galaxy dynamics hat on, it's the other way around for the same kind of reasons of a priori predictions and what comes true over and over again. So I begin to wonder if, we're saying dark matter, and that encompasses a lot of territory. And I wonder if these are even really logically the same problems anymore. But to ask
Wait, what do you mean by that? I don't understand that.
Well, so all the phenomenology that you've discussed on cosmic scales is explained in the context of general relativity plus an assumed component of dark matter, and that all works out well, right? It's just an assumption that the dark matter we need on cosmic scales is driving the dynamics of galaxies.
It's not an assumption.
It should be.
I mean,
I agree.
No, hang on. I mean, it's if you take the CMB in the power spectrum and it tells you what omega cold dark matter is, and then you do a simulation with that much cold dark matter in it, it tells you what the shapes of dark matter halos look like, and we compare those to observations. And I mean, small scale structure problems aside, they agree.
So there is a dichotomy on scale. So if we talk about the large-scale structure, for example, the power spectrum of galaxies, as you showed, that's using galaxies as basically point particles to trace the overall structure that's grown up in a way that we can trace in an elegant fashion using perturbation theory, starting from the CMB, and that's great.
Okay.
That tells us nothing about the nonlinear.
No, it goes nonlinear, so you have to
use
use in-body simulations. Fine.
Yeah. So
we know how to do
what
that.
I'm saying is another. All right. Let me give a specific example. If you would put out the figure that Douglason made of the
matter power spectrum?
Matter power spectrum.
Sure
so
thing.
if you look at McGaw 1999, there was a conference report from 20 years ago that you will see an extremely similar figure because I made the same prediction that, geez, if the universe is made of baryons, as you'd think in MOND, then you ought to see that kind of power spectrum. But even there was a caveat that MOND is a highly nonlinear theory, and you need that nonlinearity to drive the structure formation, right? Because otherwise, for the reasons you've described, you will not get here from there.
Okay.
But MOND will do that. It'll make structure grow early, and it'll probably overproduce it. So that nonlinear process will make those modes mix, and that'll wash out by the time you get to low redshift.
Well, no, I don't think so. I mean, so Scott's point is that the reason you suppress BAO and lambda CDM is that you form the dark matter perturbations and then the baryons fall into them. In Mondian cosmology, the perturbations that we're talking about are baryonic. So they should be
yes, but they've had a
this
long,
big.
Yes, I agree.
But we observe the universe and they're not that big.
But they've had a long time to grow in a nonlinear scale by redshift 0. So what I'm saying, if you asked for people to try to, make other input into cosmology, the prediction I made then, 20 years ago, is that when we could do 21 centimeters tomography and see structure starting to emerge in the dark ages already, you're going to get something more like that in a Mondian universe because there hasn't been that opportunity to wash it out yet. Okay, that's a prediction I made 20 years ago, already knowing that MOND is nonlinear. So you can't.
I know the paper you're talking about,
like,
but in that paper you have omega baryon of 1, right?
No, it's like 0.02 or whatever BBN said at the time.
Okay.
The baryon fraction was 1.
Right, of course, but we're not in a flat universe in that. So.
Yeah, and so this is another thing where things are incommensurate. Because again, I agree with you about fitting the CMB. Everybody's said this over and over again. I agree that's something any theory has to do. But as you said, the amplitude of the second peak is bang on what I predicted would be for the absence of dark matter.
Yeah, the second peak doesn't tell you about dark matter.
It tells you about the baryons, right? And the baryon density.
I think we can all agree that baryons exist.
The baryon density in the 90s was 0.019 from deuterium. It didn't go up to 0.022, which is a tiny difference that nobody worries about, until after there were CMB data. If you actually look at the history of what people
No, the CMB gives you a much better determination of omega baryon than BBN does.
Good
Agree.
barometer. But if you use, so what I'm saying is that's not a prediction. The location of the first peak had to be where it is because it's flat. That's a true prediction, and I think that's amazing. The amplitude of the second peak was what I got right without dark matter. And
Sure.
You can fit it with dark matter, but it is a fit. It is not a prediction.
Yeah, the successes of dark matter are on the 3rd, 4th, 5th, 6th, 7th, and 8th peaks. Yeah, right.
And you're totally right. I have no idea how to do that in any theory, but the same thing applies with rotation curves, unless we just ignore them because they're inconvenient.
But
you have
ordinary
to
cold collision with dark matter explains those fine.
No, I'll talk about that tomorrow.
Do we have, yes, here, Justin.
Hey, Justin.
Hi. So I guess on this issue of rotation curves and the CMB and so on, I mean, there is something to point out here, which is that Mondian type phenomenology and those sorts of theories, one of the reasons they focus so much on rotation curves is because that's where making model predictions is easiest, right? If you have a theory that predicts the gravitational force based on what you see, then you can go to a galaxy, measure what you see, and predict the force. If you don't have that theory in a cosmological context, it's much harder to make statements about the CMB and large-scale structure and so on. But I would argue the converse is also true for lambda cold dark matter. So for lambda cold dark matter theory to do large-scale structure, you're in the linear or weakly nonlinear regime, and baryonic effects are not such a big deal. But if you're asking lambda cold dark matter to explain galaxy rotation curves, what you're really asking is for us to simultaneously solve galaxy formation, and that's a hard problem.
I couldn't agree more.
And so I mean, obviously we should try to do that, and we should try to find corners of the universe where the theory can be robustly tested independently of what we don't understand about galaxy formation. But we also should be very clear about what observations are good places to test the cosmological model, and what observations are challenging for the cosmological model to get a good theory error bar on.
And 10 years ago, nobody thought you could do the hydro stuff in a way that would make these lambda CDM predictions robust, and a lot has changed in those 10 years. We made a lot of progress.
The rotation curves that are relevant here are way outside what the baryons are. Nothing to do with baryons. Look at the 1980s papers, and you see.
I'm not just talking about
the rotation
curves. I'm talking about
the
galaxy
flat
formation
rotation curves were there in my 85 paper. You don't need to worry about baryons.
Carlos, I don't know what you
affect
think I'm
the things
arguing,
in
but
the
I'm
center.
not arguing against that.
No, well, I'm just arguing about Justin that the baryons are not relevant. The flatness of the rotation curves is there way past the radius where the baryons are important, and that's been known since 85 that CDM predicts those.
Of course.
Yeah.
No one disagrees with that, Carlos.
Okay.
We all agree. Do you disagree with that, Justin?
No, I do.
Okay. Oh.
So,
Maybe I'll get out of the way.
So you can after.
so dark matter at cosmological scales and all the successes there is used in a way where it's only featuring as a pressureless, collisionless matter.
Right.
So anything that behaves like that effectively would do exactly the same thing.
Sure.
So I think that if you have a really can combine the successes that Mond would have at the galaxy scale with what lambda CDM does, if that would be possible, that would be the ideal world, because then you can. So if it's possible indeed, and this is sort of what I hope, if I can calculate the dynamics of what I described, that the effective description of what's going on in that behaves like pressureless, collisionless matter, I can use a lot of even the equations that are used without having it being dark matter in the sense of being a particle or anything of that sort. That's not necessary for the cosmological successes.
So maybe this is a semantic.
It's assumed there that it must be a particle of some sort. It has to behave effectively as pressureless, collisionless matter.
So this might be a semantic issue, but if you tell me you have a theory and it includes something that behaves like a collisionless, cold fluid, let's say, gas, that has keeps a fixed quantity of energy per co-moving volume, whatever, that sort of thing, I would call that dark matter. Maybe somebody else wouldn't, but
I emphasize the word effectively. I mean, there's some way that the gravitational equations have to generate this effect, but if it behaves effectively like that, I mean, that would be a way of combining the way. But anyway, this is my point is that it doesn't really require GR in the same to be the theory up to that point. I mean, there may be ways in which the modifications to GR may effectively behave in that way.
How would you rule out your theory? There's just one way.
I had it on my slides.
How do you rule out your
Detect
theory?
dark matter and show that it has all the properties that it should have.
Sorry?
detect dark matter. If you detect dark matter,
Oh,
then
I see. I have a question. Dark matter is a hypothesis, but it's easy from the standpoint of elementary particles, from the standpoint of an elementary description. It's easy to come by particles or primordial black holes, candidates that will have attractive gravitational interactions, may or may not ever interact with the standard model sector, so we may not detect it, but it is conceptually easy. But you are portraying, as far as I understand, a type of dark energy, and you call it dark energy, I guess, because it is not matter, namely doesn't have attractive gravitational interactions, and behaves in a very particular manner with elasticity and so on. From the elementary point of view, what kind of elementary description do you have for this type of dark energy?
Well, that's a difficult question. I mean, I've told you that I didn't want to go into all the details of what we're doing with quantum information, tensor networks, and all the stuff that we're doing in thinking about emergent gravity. That's a complicated story. But there is a microscopic story in string theory in which we understand entropy of black holes, and the same way we can describe things in dark energy. So there is a microscopic story, and it goes beyond just particle physics and quantum field theories that we've been using in the 20th century. This is really a theory that goes a step further. So the language is different. I already made that clear on the slide, and I didn't want to go there, but that's the way that it's going to be described.
So how do you get the repulsive gravitational interaction part of it? Because everything that we can think of, right, except dark energy or maybe a scalar field, vacuum energy associated with vacuum energy doesn't have repulsive gravitational interactions.
So that's the thing one needs to explain, but anyway, I cannot answer this in this question session in this way. I mean, I cannot explain the equations or even the concepts in the short time I have. What I wanted to say is that oh yes, I mean dark matter, I mean when it's a particle says nothing about dark energy. What I'm trying to argue is that the two solutions have something to do with each other. And of two problems, and the solving the problem of dark matter and dark energy are related. So there is a connection between those two. And so this is where I think that conceptually, I think there's a very big difference between the way I want to get to these, to explain these phenomena than what happens in a dark matter scenario with particle dark matter. I mean, particles is one part of then the world, and dark energy would be unexplained and a totally different part of that.
So we've been contrasting cosmology with galaxy dynamics, but there's a set of measurements that we have made on intermediate scales that is instructive, and that is on 100 kiloparsec to 50 megaparsec scales. We now have, with millions of galaxies, measured the enclosed mass via galaxy-galaxy lensing. And so there's a lot of data there that is consistent with the standard hypothesis. I won't call it a theory, which is consistent with both the galaxy dynamics and the cosmology. That is to say, we see galaxy dark matter halos. We all go all the way out to the halo term, and then finally out to clusters of galaxies with the lensing.
Couldn't agree more.
So I work on dark matter, but here a bit provocative one, a bit open a gap in what Eric says. Like, what I'm interested in, okay, is it a particle? Yes, I'm interested in doing that. But I actually myself want to know what is space-time, what is really guiding our universe. And even whether true or wrong, going that way may open up way more gaps than finding a particle in other questions we somewhere have. And so the operative question of what is dark matter, or what type of particle it is good, but it may not open that gap. Who knows? Yeah, but
the issue is that ideas are, of course, what drive this physics, right? Ideas, but we can only compare things that make clear predictions, and I don't think that we are at this stage. So the idea that gravity may fail us, actually, the general relativity is not the final, well, that's a very appealing thing, but every concrete idea, for example, nonlinearities, well, use your nonlinearities, make a complete model, make your predictions, and then we compare with data. This is extremely far from there, so interesting directions and saying, oh, dark matter is not there, is a very different kind of a statement, right? This is what I think.
Yeah, I mean, I would say, from my point of view, trying to replace the particle dark matter framework would mean reproducing a lot of its successes and doing all that in a complete way. asking the fundamental questions about what's going on with the global structure of space-time, what's going on with dark energy. Those are fundamental questions that have independent merit, are independently interesting, are maybe have something to do with this complicated dynamics. And so I think there's some way in which it might be compatible to have particle dark matter as well as some breaking GR vision of how dark energy comes about. It's a little bit hard to see to compare how whether or not that ultimate replacement for dark energy for the global structure of space-time, does that come part and parcel with this kind of prediction? And if so, then these things would be incompatible. If it doesn't come part and parcel with it, if that's something that's extraneous, then maybe we still have particle dark matter at the end of the day and all of its successes, which is appealing.
You just said we should take predictions seriously and confront with observations, which of course everyone agrees with. And on that note, putting up that picture of the bullet cluster is a little dangerous because you don't actually expect that to happen in cold dark matter cosmology.
Of course you do.
If you calculate the odds of finding a system with that, with the initial conditions that will give you the bullet cluster, the approach velocity 3,000 kilometers per second at a initial separation of 5 megaparsecs, the masses of the two clusters involved, and you interrogate a Hubble volume dark matter simulation like dark sky or something, the answer that you get is up to the redshift of this object, which is 0.3. You would not expect to see more than 0.1 such collisions. Okay?
Things that are unlikely at the 1 in 10 level don't bother me. Things that are unlikely at the 1 in 10 level don't bother me.
And you have written in parentheses, and its cousins. This is not the only such object now. Of order 10 such objects have been found. 100 more are in the pipeline from radio surveys waiting to be analyzed, have redshifts measured. So I think the case is building up that we are seeing things on the sky that really shouldn't be there, according to the expectations which Graciela rightly reminded us, should be taken seriously and confronted with data. So whereas your basic point that this is clearly visual evidence that there is dark matter as reconstructed by lensing as distinct from baryonic matter, that point is well taken. But if you are going to be serious about this business, then these anomalies should not be brushed under the carpet. They should be investigated more closely.
Anyone who knows me and how I do science knows I do not brush anomalies under the carpet.
I'm not saying you are.
No one has ever accused me of that.
Well, fair enough. But I just heard George say, yes, we expected this. No, we didn't expect this.
I of course agree, Samir. I of course agree.
I think the point here is that gravity does not seem to trace baryons. That's the only point I think Dan is trying to make. And that is compatible, I guess, with many ways of thinking about it, one of them being collisionless dark matter. And also by taking one example and trying to milk it for all of its worth, I think we'll always make the mistake of going with a posteriori statistics. And then you find something that is rare, and then you find that it's very unlikely. I say, look at your spouse and say, if I were to rerun the history of the universe again, will I marry the same person again? The answer is no, trust me. And the probability is 10 to the minus 120, all right? Bigger than the entropy of the universe.
Does your wife know this?
So that's a reason why I haven't married again, but anyway.
What's the point?
So I was just going to say that on a somewhat similar vein, we talked about the small-scale structures as being, maybe some problem for CDM, but actually I think that there's opportunities there that's actually further evidence for particle vision of dark matter in the sense that you can look at, say, globular clusters and at ultra-faint dwarf galaxies and see, huge discrepancies in the mass-to-light ratios, for example, even though their stellar populations are similar. And I guess at least in principle, there's a possibility in the next couple of years that we could identify purely dark matter subhalos. And it seems like that would be pretty compelling evidence for particle vision of dark matter.
From lensing?
Yeah, from lensing or from dynamics of some kind, like stellar shooting gaps.
From Gaia velocities, for example, you could infer the presence of a subhalo without stars, for example.
In the gaps, there's
The gaps are one. Well, there's not the only way.
Well, gaps are lensing. What other ways?
You notice all the velocities in the disk in one place are all kind of perturbed upward, for example. That's in some.
Yeah, my point is that there are gravitational signatures that would point to pure dark matter objects.
Okay, so we should all of us try very hard and find any other interactions with that kind of particle, and just as Eric will have this concluding argument about all this